Okay, last time we had defined this propagator, which is basically the vacuum expectation value of the time order product of two fields, phi x prime and phi x. The fields are at two different space-time points. Okay, and this we can write as, which we also saw last time, as theta of t prime minus t phi of x prime, phi of x plus theta of t minus t prime, phi of x, phi of x prime. Okay, and this quantity we called d of x prime x d of d x prime, and we found that it was translationally it was invariant under translations, and that's why we had put x prime minus x plus theta of t minus t prime d of x minus x prime. Okay. Also we saw that d of x prime minus x is d4k over 2 pi to the 4, and then we had a delta function with the delta plus k square minus m square. Okay, and then we had e to the minus I k dot x prime minus x, where let me remind you that delta plus is basically k square minus m square is just a shorthand notation for writing theta of k0. Okay, which means this quantity is non-vanishing only when you have the sign of k0 as positive. Yes, theta is the unit step function, this one. This you have if theta of x minus x naught, and this is the point x naught. Okay, in this case this is theta of, sorry, what I meant to draw is this. This goes to infinity, okay, extends to infinity, and this is the point x naught, and this is theta of x minus x naught, some point x naught. Okay, that's the step function. And we also saw that this object dx prime minus x is Lorentz invariant, and it's easy to see. So if you do a transformation of x prime minus x to some lambda of x prime minus x, meaning you do a Lorentz transformation and go to another frame. So here this will go to lambda of x prime minus x, but then you can do a change of variables and go from k to lambda k. If you do so, this will be k dot x prime minus x. Okay, this will go to this way. This object x prime minus x has anyway gone to lambda times x prime minus x, and k will go to lambda k, and this, you know, it's a Lorentz invariant object, so this will come out to be x prime k times x prime minus x. Okay, and then we saw that these pieces are anyway invariant, so k square remains unchanged when you go from k to lambda k, and d4k also remains unchanged. So you can relabel the variables and again get back the same equation. Okay, so this we saw that this is Lorentz invariant. Let me remove this. Okay, now what we want to ask is whether df x prime x, this is also Lorentz invariant object. Okay, that's the question. is, first let me write down Lorentz invariant, and our question is dx, the propagator dx prime x also invariant? Okay, and that's what we are trying to do in this video. What happened? Oh, that's strange. Okay, now it's back to normal. So that's the goal, and what I want to do first is look at dx prime minus x. That's what I want to look at, and see what it is explicitly when the interval between x prime and x is space-like. Okay, so consider x prime minus x square to be less than 0. Okay, that is, we are looking at a space-like separation. Okay, and then let's see what happens to this object. So this is yeah, I had missed the 2 pi to the 4 in the previous expression. Let me put it here. So here we had a 2 pi factor also. Let me write it down outside the integral. Okay, so we have here this thing d4, let me write dk0 d cube k, that's our d4k. Okay, and I am splitting the factors of 2 pi like this, and the integration limits are from minus infinity to plus infinity. Okay, and here also from minus infinity to plus infinity in both the cases. Then you have 2 pi delta of k0 square minus k 3 vector square minus m square, and then you have theta of k0. So that I can use here and put the limit from 0 to infinity, right? Because now you have a support only from k0 equal to 0 to infinity. So if your k0 is less than 0, all the integrand vanishes. So that is why I have put the limit to be 0 here. And then you have e to the minus I k dot x, which is k0 x0 minus the dot product of the 3 vectors. Okay, that is fine. Okay, let me write one more step. E to the minus I k0 x0 d cube k not necessary that I do this, it looks a little bit neater. Okay, so that's what we have. Now I want to look at d of x minus x prime. So I am changing the order. Okay, now if I change the order, then I will have just like what I had here, integral 0 to infinity dk0 over 2 pi e to the minus I k0. Something is wrong. So here I made a mistake. So this is e to the minus I k0 x prime minus x0 minus k dot x prime minus x. That's what we have, not this. Okay, and here also this will be x prime 0 minus x 0, and this will be x prime minus x. Okay, so let's look at this one now. X0 minus x prime integral, and these limits are minus infinity to plus infinity, to pi cube, 2 pi, same thing again, and then we get e to the minus e to the I k dot x vector minus x prime vector. Okay, just the order is interchange, exactly the same thing. Okay, but this piece is, if I interchange the order, I can write it as e to the minus I k dot x prime minus x. Okay, so the argument here, the x prime minus x is same as here. Okay, the only difference between these two is minus sign. Okay, that's fine. Now what I can do is I can do a change of variable and go from k to minus k. Okay, which means that kx goes to minus kx, ky goes to minus ky, kz goes to minus kz. Okay, and if you do that, then your d cube k, which is basically dkx, dky, dkz, will go to minus d cube k. Okay, and the integration limits will go from, instead of minus infinity to plus infinity, they will get reversed. They will go from infinity to minus infinity, right? But then you have an overall minus sign here, and each integrand, integral limit you can interchange again, because using this. So let me write explicitly. So dk, if you take k to going to minus k, it will become minus dk, and infinity to minus infinity, you can take this infinity and interchange the order, so which is same as minus infinity to plus infinity dk. Okay, so you get back the same thing. So under k going to minus k replacement, okay, this remains the same, this remains the same because this is squared. This gets changed, you get a plus sign here, which is what you had earlier for dx prime minus x, so it becomes the same factor like this. So from here to there, this place, you get exactly the same if you change the variable from k to minus k. Okay, so this piece will be identical because this will change. So let me write it down. So you get 0 to infinity dk 0 e to the I k0 x0 minus x prime 0 into a piece which is same in the same as above one, same as this one. Okay. Say in general dx prime minus x and dx minus x prime are not same. Okay, they are not same because of the difference here. Here I cannot take k naught to minus k naught and get the same thing as here. That's not possible. Okay, that's not going to happen. So there is a minus sign here. So you see, you have x prime 0 minus x 0. Here you have x 0 minus x prime 0. So there is a difference in sign here. But now the limits are not from minus infinity to plus infinity, they are from 0 to infinity. So that makes a difference, which makes that dx prime minus x is not equal to dx minus x prime in general. Okay, that's the general statement. But now we are going to use the fact that we have already shown this object to be a Lorentz invariant object, meaning I can calculate this in any frame, whichever I wish, and the value would be the same in all other frames. Okay, so that's what I'm going to utilize to make a statement about what happens when x prime minus x is space-like. Now, if the separation between two space-time points is space-like, it means that allows you to go to a frame where they happen simultaneously. Okay, there is no notion of which event happened first and which event happened later if the events are separated by a space-like interval. So, I can go to a frame where t prime is same as t. This is what I call t prime and this is what I call t. I should have used that. That would have been a bit neater, but anyway. So I go to a frame where t prime is t or x prime 0 is equal to x 0. So, let us do that. So, go to dx prime minus x is Lorentz invariant, can be calculated in any frame. And of course, the value will be same in all the frames. Okay. And because this is space-like, so I am choosing space-like interval. Okay, I am looking right now only at space-like intervals. Because so not because, let us say for space-like interval, I can always set x prime 0 is equal to x 0. Okay. So, I will go in such a frame, and that is useful because if I go into such a frame, then this thing is 0. Okay, x 0 minus x prime 0 is equal to 0, and the same thing here. So, the piece which was giving a difference just drops out. So, it becomes e to the 1 which is e to the 0 which is 1. So, we get then integral 0 to infinity dk 0 over 2 pi, this is 1, and then you have this piece which is same in both the expressions. So, you see that for space-like interval, dx prime minus x is same as dx minus x prime. Okay. But this is of course not true for time-like separation between x prime and x, because then you cannot set this to 0. Okay. If they are not at the same time in some frame, then they are not going to be at the same time in any frame if they are separated by a time-like interval. Okay. But for space-like interval, that is good, we can show this equality. And now this will be useful to make some statements about df of x prime x. Now let us write it back again. This was theta of t prime minus t. So, let me write down t prime is x prime 0 and t is x 0. And we had d of x prime minus x plus theta of t minus t prime d of x minus x prime. Okay. So, let us take first the case where x prime minus x is space-like, the interval is space-like. So, for such a case, this and this, they are equal. Okay. And if they are equal, I can just take them as common, and then what I have here is theta of t prime minus t plus theta of t minus t prime. And what is that? Sum, that is unity, that is 1, because you see here. So, let us choose this to be t and choose t prime to be something. So, you see one function gives you unit when you are below this, the other theta gives you this one gives you this. Okay, one is giving you this, the other theta is giving you this. So, the sum of the two is 1 all over. Okay. So, this is identically equal to 1, which means df. So, this is equal to, okay, this is so for x prime minus x square less than 0, df x prime x is equal to d of x prime minus x. Okay. Now, if this because this object is Lorentz invariant, it means that df x prime x is also Lorentz invariant if the interval is space-like. Okay. And because this depends only on the difference of x prime and x, df, the propagator, also depends only on the difference between x prime and x, and this we have shown for space-like separation. Okay. So, let me write down. So, we conclude here that df x prime x is Lorentz invariant because this object is for x prime minus x square less than 0, and also it depends only on the separation x prime minus x, because on the right hand side the dependence is only on x prime minus x and not x prime and x individually. So, this has to be true for the propagator also. That is what we have shown. Now, let us ask what happens when the separation between x prime and x is time-like. So, it is greater than 0. Okay. Now, let us see. You have df x prime minus x is equal to theta of t prime minus t, d of x prime minus x plus theta of t minus t prime, d of x minus x prime. Now, this is Lorentz invariant, this is Lorentz invariant. Okay, this we have shown already, irrespective of whether the separation is time-like or space-like, this is always Lorentz invariant. This object, this one and this one, these two are also Lorentz invariant if the separation is time-like. Remember, the sign of t prime minus t is invariant if they are separated by time-like separation. So, this is also Lorentz invariant, this is also Lorentz invariant, which means that the right hand side is Lorentz invariant. Okay. So, what we have shown is that df, and also here you see that it depends only on the separation between x prime and x and not individually. So, what we have shown is that we can write the propagator as, okay, the argument will be x prime minus x, and we have also shown that this is Lorentz invariant in general. Okay, no matter whether the separation is space-like or time-like. Now, our next target should be to find out the expression for the propagator, and this is what we will aim in the next video. Okay. So, see you in the next video.